start with today's lecture. And as I mentioned, today's lecture is basically going to be a new topic, which is your sampling of discrete time systems. Sampling, what is sampling? All the details regarding sampling that is going to be covered here. So what all topics are going to be covered? So how do we sample? What is Nyquist rate? How do we reconstruct? These types of topics will be covered in this slide set. So signal system, this is basically chapter 7, those of you following MIT lectures starting from 9 or 13. So starting with the actual topic, what is discrete time sampling? So this is our today's topic. And in this, we are going to cover details regarding sampling. Again, any questions so far, whatever we have covered in previous lectures?
Sir.
Ji, Osama, you wanted to say something?
Yes sir. Sir, क्विज में आपने फ्रीक्वेंसी हर्ट्ज में दी हुई थी, उसको एज हम एफ लेंगे या एज एन ओमेगा लेंगे?
You see, generally whenever we are talking about angular frequency, that is omega. If you're talking about Fourier deals with omegas. Omega is 2 pi f. So frequency in hertz gets converted into 2 pi times that much. That is your omega. And again, whatever you have done, I'm going to see that. So by now you should be clear that what is frequency in hertz, what is frequency in radians per second, what is complex frequency. So at times we engineers tend to use the term frequency for all these. Complex exponential is also called frequency. Again, this angular frequency is also called frequency, and frequency in hertz, as we know, it is also called frequency. So we engineers tend to use this term interchangeably, but once the hertz is mentioned, that means we are talking about frequency in hertz, that is f, and that can be converted into omega. And if you're talking about complex frequency, then what it means, you should know that. Okay, any further questions? Any further questions? No further questions. Let me go over your quiz, because people, one question on the quiz. Let me just quickly see what we had. I believe this was your quiz, if I'm not wrong. Is that right? This was the quiz?
Yes, sir.
Okay, so if you see this, this was what was asked for, and let's see that how we can do this. So we were given this square type of pulse, and we have to find out frequency content in x of t, and we have to find out magnitude of 100 hertz frequency. This is what people are referring to. This is f equal to 100. You can call it f1, whatever. And if you're talking about omega, it will be 2 pi into 100. So this is what this thing is. And time given, I think a lot of time was given for this. So how do we find frequency and how do we go about this? This is just going to give you a very simple sync that we already have seen. And how do we find that out? We can simply go from x of t to xj omega. And let's do this. So xj omega is just going to be your integral minus infinity to infinity x of t e raised to power of minus j omega t dt. Simply this. And if you see the values here, it is from minus 1 second to minus 0.1 to 0.1 seconds. So we know that the value of x of t is 0 only from minus 0.1 till 0.1 seconds. This is 1 e raised to power of minus j omega t dt, and then you can just see what this comes out to be over what should it be, minus minus j what omega? Please speak louder. I'm not able to hear you guys.
Yes, sir. Minus j omega.
Okay. From minus 0.1 to 0.1. And this will come out to be, we can take this 1 over minus j omega outside, and inside you'll be left with e raised to power of minus j omega into 0.1 minus e raised to power of minus j omega into minus 0.1. And then we can just take 2j plus minus, okay, 2 over minus omega, we can just take it inside, and we end up getting, sorry, this also we can take inside, so we get e raised to power of j omega into 0.1 minus e raised to power of minus j omega into 0.1, whole thing divided by 2j, which we know is going to be your sine. So it is going to be sine 0.1 omega, whole thing divided by 0.5 omega. This is what you're going to get. This is your xj omega, your frequency contents. This was the first part. This was the first part, find out the frequency content. So we found out xj omega. So these are the frequency content, which is this. And we know that if you want to plot this, it is just going to be a sort of a sink. This is a sink. Xj omega against omega. This is going to give you a sink value. And this will be 1 and all that. Okay, so if you want to find out the second part said the frequency magnitude of 100 Hertz frequency. This was something that we need to find out. So 100 Hertz omega 1 comes out to be 2 pi into 100. So what is your xj omega at omega equal to 2 pi 100? So this we can just plug in value, which will be sine of 0.1 into 100 into 2 pi, whole thing divided by 0.5 into 2 pi 100. And whatever that value comes out to be, even if you have done this, this should be good enough. This is going to be your value at 2 pi 100. So xj omega at omega equal to 2 pi 100, this is going to give you the value of this thing. And this is value at 2 pi 100. And similarly, we can find value at minus 2 pi 100, which will be again the same thing with omega equal to minus 2 pi. So remember, each point, the 2 pi 100 point that we are seeing, the value that we are finding out, this will be equal on both sides, and they together will give you a single frequency. They together are going to give you your single frequency, that is at 2 pi 100 and 2 pi minus 100. I'm sorry for this shake here. So this is what will be the end result. Okay, so it is just showing you that what that quiz actually was. Now coming back to our topic for today, which is sampling. Now in sampling, what is sampling we already know. This is actually taking your sample values at equidistant points, T2, T3, T. If you take these points and put the values here and against n, then that will be your sampled version. So to sample, we just take value at particular sampling period, let's say t. So this sampling, by common sense, we know that we just take values of the signal at some equidistant points, and this distance that we select, this time period t, is that distance that we select. That is the interesting and important point, that at what rate, at what distance should we sample. For example, if we select t equal to, let's say, 0.1 seconds, that means in 1 second we are going to have 10 samples, or 10 samples per second, because sampling frequency is just going to be 1 over t. So it will come out to be 10 hertz or 10 samples per second. If it is 0.01, it will come out to be 100 samples per second. So this is how we actually do sampling, and the values that we get, we can store them, or we can plot them, or we can write it down on a piece of paper, and we end up getting x of n. This is what sampling is. This is how we sample a continuous time into discrete time. Now, this type of sampling and getting your discrete signal is widely applied in digital systems, and we do digital analysis of those systems. In real world, most of the signals are continuous in nature. So continuous time signal, x of t, we first sample it at a particular time period t and get your x of n. This is your discrete time signal. And once we have got our discrete time signal, then it becomes very easy for us to do whatever manipulation we want, to do whatever analysis we want, and get our desired value y of n. And once we have got our y of n, then we can always reconvert your signal back. We convert your signal back into y of t. An example is that of audio system. In audio system, for example, if you want to amplify, then one way is we can build a continuous time amplifier using all those transistors and class A, class AB, and whatever type of class C amplifiers, and then amplify your signal. The other way is we can convert that audio signal into first discrete time signal. So audio is first converted into discrete time signal, and then we amplify, and then we can convert it back into audio signal, and then we can hear it. So although this seems like a lot of doing, we can simply have an audio system, analog system. But building an analog system is always problematic, and building or working in discrete or digital domain is very simple. For example, amplifier system, if you want to amplify 2 times, this system is just multiply by 2. So whatever sample values you have, we just multiply by 2 and get y of n. It is as simple as that. You want to change amplification value, you multiply by, let's say, 4, multiply by 10, whatever. So amplification is as simple as that. Just a simple example of why people like to work in discrete or digital domain. So samples of continuous time signals are taken to get your x of n. Then we design and process your discrete time signal to get our desired output. And then for real world, we convert your discrete time back into continuous time. So this is what is done all the time in real world. Why is sampling important? We have covered it so many times. I just gave you one example because it is much easier for us to work with discrete time systems. And as it is mentioned here, many systems use different types of tools like MATLAB and all that, where designing and processing discrete time systems is very, very simple for us. It is much more efficient and more general compared to performing continuous time system design. So we can easily work with discrete time signals. It is much easier for us. Otherwise, also storage is easy and reproducibility is easy, and so many different benefits are there. So that is why sampling is important, or conversion of continuous time into discrete time is involved. And we can use Simulink to perform simulation, and we can do so many other things. Last few decades, dramatic development in digital technology has resulted in very cheap, lightweight, programmable, reproducible discrete time systems which can be built. And these discrete time systems, like we have this MP3 players, like we have this audio video players. So all of them are basically discrete time systems which work with discrete signals and give output, which is again discrete time output. And then to visually see video or hear audio, we have to convert back into continuous time again. So first we convert into discrete time in these systems, and then these systems work with those signals, and the outputs again converted back into continuous time. This is what is happening in real world in almost all the systems, digital or discrete systems that we come across. Cameras, video cameras, static cameras, audio players, multiple different devices. Okay, now coming over to how do we sample? As we saw, sampling a continuous time signal is quite straightforward. We take samples at equidistance point t, 2t and all that and get all those values. Now, the problem is that at what rate should we sample? What should be this distance in between the samples, this time period t, the sampling time period? What should be the appropriate sampling time period? How many samples should we take per second? This is an important aspect. The sampling time period, or in other words, sampling frequency, that's one and the same thing. So sampling frequency is how many samples we are taking per second. So this is very important. So how do we actually come up with that value of sampling frequency or sampling time period? This example actually shows three signals, x1, x2, x3, one colored green, then red, and then blue. So if we take this as 1, this as 2, and this as 3 different, let's say, signals. If you sample at this particular time period t, which is selected, you see each of these three signals end up giving you the same x of n. Now, if we want to reproduce back our signal, we'll be able to reproduce your x2, this red one. But these green and blue ones, they cannot be reproduced if we sample at this rate. You are going to end up getting a changed signal, which will be your red signal, even if you start with blue or green signal. Now, how do we actually make sure that we get our original signal back? This is what we engineers are supposed to know, that what is the right sampling duration or sampling frequency. Now, here, one thing we can see from common sense, that if the signal given to us is basically having some max frequency, and then if the samples are sufficiently close, in other words, if your time period t is sufficiently low, or this distance between samples is quite close to each other, then it will be possible to uniquely reconstruct your original continuous time signal from sampled signal. Otherwise, it will not be possible. So how close should this time period t be? How close these samples should be? So in other words, how high should the sampling frequency be? This is something which we need to somehow find out. Because if we don't select the right sampling time period, you will not be able to reconstruct your original signal back. So this much we know. Now, to understand the sampling, we first study what is known as impulse terrain sampling. This is a theoretical sort of sampling. It is just theoretical. But this gives us sort of an insight in the sampling process, that what happens once we sample. And this impulse terrain sampling, what is impulse terrain sampling? Let's see. In this, the given signal x of t, whatever that signal is, this is multiplied by an impulse terrain pt. This impulse terrain pt is basically the main thing with which we do impulse terrain sampling. This is basically a infinite set of impulses, each having value 1. So you can see that these are all delta t's, which are shifted and having spacing of t in between. So lies at 0, lies at t, lies at 2t, and like that it goes on. So duration in between these impulses is equal to time period t. What is that time period? That is our choosing. We can select any time period. So impulse terrain is a infinite set of impulses spaced at time period t. So if this is delta t, this is shifted version of delta t, this will be delta t minus, this will be delta t minus t, the other one will be delta t minus 2t. So these are different impulses that we have right here. This is delta t, this will be delta t minus capital T, delta t minus 2 times capital T, like that. And similarly on this side will be plus side, delta t plus t, and like that. So these are basically set of impulses, infinite set of impulses. And if you want to represent mathematically your impulse terrain P of t, this is basically delta t minus a multiple of t. And this multiple is anything from minus infinity to infinity. We can expand it and write it like this. We have delta t plus delta t plus t plus delta t plus 2t, and like that it goes on and on and on. This is what we have right here, and similarly on the other side we have delta t plus t, and on that side goes on and on. So we can just write it as this, any multiple, and this n can be from minus infinity to infinity. This is your impulse terrain. Now in impulse terrain sampling, this impulse terrain P of t, which is set of impulses, set of unit impulses spaced at time period t, this impulse terrain is just multiplied with your original signal x of t, and the end result that we get is your xpt, or impulse sampled signal. So this impulse sampled signal is obtained by just multiplying this infinite set of impulses with your original signal. You will see that the end result will be the scaled impulses whose duration will depend on duration of your signal itself. So signal starts from, let's say, -5, ends at 5. So your impulses that will result would be again from -5 to 5, and spacing in between them would be t, and the value would be scaled according to the signal itself. Now if you take these values are basically your discrete time signal, but if you just plot these impulses, xpt will be what is known as impulse sampled signal. So this type of sampling, where we multiply your continuous time signal with an impulse terrain and get scaled impulses, is known as impulse terrain sampling, and the signal that results is impulse sampled signal. So note that this impulse sampled signal is still a continuous time signal. If you can just jot down or record the values of these impulses, then those values will be your x of n, or discrete time signal. So right now we are just talking about impulse terrain sampling and impulse terrain sampled signal. There are basically three aspects that we will see in this impulse terrain sampling. One is what happens in time domain. In time domain, this is what happens. Your time domain signal can be plotted against time. So we have this x of t, we have this impulse terrain pt. We multiply these two together. This multiplied by this gives you xpt, which is this. So this is graphical representation of what is going on. So this is the first thing that we saw in impulse terrain sampling. The second thing is what is actually happening in the frequency domain. That is what we're going to see in a few moments. And third aspect is we write equations for what is happening in time domain, what is happening in frequency domain. Like in time domain, this is what is happening. X of t is getting multiplied by p of t, and p of t, we can write it in equation shape as this. P of t is set of shifted impulses. So this is what p of t is. And t is the sampling time period. The distance in between these impulses is t, which we call as the sampling time period. And sampling frequency can be obtained by just having reciprocal of time period. And similarly, we can have angular sampling frequency, which is 2 pi over t. So this is your impulse terrain sampling in time domain, and this is sort of equations. Now if you want to write equation for xpt, it is just xt multiplied by pt. If we just plug in value of pt right here, it will end up becoming this. So xpt is basically your x of t multiplied by p of t, and p of t was basically your delta t minus n times t, and this we can take x of t inside and we end up getting this. Now inside summation, if you have delta, then values of x of t or value of this product will exist only where this delta value is 1. So only at nth multiple of time period t will we have value of this product. So that is what we see right here. Only at nth multiple at t at 2t we have value of this product, which will be the value right here. So we can just write it this way. So this is your impulse sampled signal written this way. Now coming over to analyzing in detail this impulse and sampling. First thing we need to see is this P of t itself, this P of t. It is basically infinite set of impulses. Now P of t we notice is a periodic signal. So we can write a Fourier series for this. And if you want to write Fourier series, we have to first find out the coefficient of Fourier series. That we find out using this formula AK. And we know that Fourier series coefficient are basically 1 over t integrating over a time period of your signal, which in our case is pt, e raised to power of minus j k omega naught t dt. This is how we find your coefficient, and this is integrating your signal, periodic signal, over one time period only. So the first thing we need to see is what time period should we select. So we select time period from minus t by 2 till t by 2, where the value will be just delta t. This is just selecting one time period of this from minus t by 2 till t by 2. This is one particular time period, and in between that we have just delta t. So from minus t by 2 to t by 2 the value is just delta t, and this is what we end up getting. And this integration, if you see, this product has to be evaluated from minus t by 2 to t by 2, but we know that delta t value is 1 only at t equal to 0. Only at t equal to 0 is its value 1, and at t equal to 0 this whole thing also is 1. So this whole thing ends up giving us value equal to 1. This value is just equal to 1, this whole integration. So AK ends up coming out to be 1 over t only. So that means the coefficients of periodic series is just 1 over t. Now let me just show you the same thing on some blank slide. Let me just take a blank slide and try to show you there. Okay, so what we were seeing P of t, which was basically sum of your shifted impulses t minus n times t, and here your n was from minus infinity to infinity. So this was your P of t, and what we wanted to find was your Fourier series for P of t. The Fourier series of P of t would be summation ak e raised to power of j k omega naught t, and this will be for k equal to minus infinity to infinity, and value of ak is going to be 1 over t integral over a time period of P of t e raised to power of minus j k omega naught t dt. This we have just evaluated. This came out to be equal to 1 over t. So ak came out to be equal to 1 over t. That means all these complex exponential has value equal to 1 over t. Now we can represent this ak against k. This is a representation of Fourier series, and we notice that all of them has got value equal to 1 over t. It's just 1 over t and 1 over t and 1 over t, and it just continues at plus minus 1, at plus minus 2. So throughout it is just going to be 1 over t. So this is Fourier series representation of your P of t. Remember, your P of t was basically an infinite set of impulses spaced at time period t. This was your P of t going here and going here. This was not t. So Fourier series will end up being something like this. Now, if we want to find out the Fourier transform, this will be Pj omega. What will this be? Now, to find out Fourier transform, there are about 2 or 3 ways we can find Fourier transform. First is we can simply apply the formula for Fourier transform from minus infinity to infinity, phi of t e raised to the power of minus j omega t dt, and then find out value and then plot this. There is another way where we can take Fourier transform, and that another way we know that this ak is sort of an equivalent for your Pj omega. So if we have this omega axis, this k axis, 0 corresponds to 0, 1 corresponds to your omega s or minus omega s. You can call it omega naught or whatever. So this is basically the fundamental frequency. So then if here we have 1, here we will have 2 pi. And here it is 1 over t, here it will be 2 pi over t. So similarly, on this point only, this will again be 2 pi scaling in. So you will see that you will end up getting just this. So we can directly translate from ak to this thing, and you will see that we have a scaling factor of 2 pi and we end up getting this thing. So this will be Pj omega, and we can write this Pj omega. These are just set of impulses, and the value of these impulses is basically 2 pi over t, and the spacing of them is again omega s, and notice omega s is what? 2 pi over t. So if this thing is 2 pi over t, we can also call it as omega s. So this is basically an impulse on omega domain. So an impulse on omega domain, how do we write an impulse on omega domain? Sorry, we're getting this shape thing. It is just delta omega. For example, let me write it here to just better here. For example, if you have an impulse on t axis, this is just delta t. If you have an impulse on omega axis, it will be delta omega. Now a shifted impulse or shifted by omega s would be delta omega minus omega s. So if you have multiple of these, we can just write it as this. We have delta omega with the value of omega s, plus we have omega s times delta omega minus omega s, plus we have omega s times delta omega minus 2 omega s, plus goes on. Similarly, on the other side also we have omega s into delta omega minus omega s. So these are set of impulses, and if you want to just write it as summation, this will be just summation and delta omega s minus n times or k times, whatever you want to call it. Sorry, this is omega minus so it will be just a set of impulses which are equally spaced, or the spacing is I'm sorry, I'm just getting trouble with this. Okay, so this is basically what you end up getting, and outside we can take omega s, and this will be k equal to minus infinity to infinity. So this is going to be your Pj omega. So this is your impulse terrain. Your impulse terrain being periodic, we can find Fourier series for this. Fourier series coefficients are this, and from Fourier series we can just jump to Fourier transform, and we can see that how we can jump there, and we end up getting value right here. So this is one way, which is kind of a novel way of finding Fourier transform, but a very simple and easy method of finding Fourier transform for periodic signal. If you have periodic signal, we can find Fourier series, and from Fourier series we can find Fourier transform just by inspection and just by conversion of AK into your Fourier transform. The other is putting it inside the formula. Now putting it inside the formula also is not that complex. Reason being, your PT is set of impulses. That again, if you just put it this way, your PT is basically nothing but set of impulses. T minus n times t, and these are basically n equal to minus infinity to infinity. This was a PT. So Pj omega, we can directly find out minus infinity to infinity. Pt e raised to power of minus j omega t dt. Plugging in value, it will be just integral from minus infinity to infinity, sum of n equal to minus infinity to infinity, and we have this delta t minus n times t e raised to power of minus j omega t dt. So this is what we end up getting. Now inside the integral, if you have delta, then end result would be just the value that you see at delta point. Now this delta function is going to be 1 at t equal to multiple of n multiple of time period t. Only at that point it will be 1. So we can just replace this with these complex exponents, and we will end up getting the same thing that you see that we had earlier. This thing, these impulses. Now notice that how this impulse is related with complex exponents. These are one and the same thing because each point here is basically a complex exponent also. So an impulse relates to complex exponent. So this is something which will become more clear as we go on. So right now, just coming back to what we were covering earlier, the slide set. Here we see we can directly find out Fourier transform, which will be omega s delta omega minus k omega s. They have kind of skipped multiple points that how we get from ak to pj omega. So if you just plot ak, which is all 1 over t, so you will see that we'll end up getting this particular set of impulses. So this is your pj omega, and your Fourier transform of xpj omega, your Fourier transform of impulse sampled signal. So what will that be? So here we saw p of t Fourier transform was pj omega. Xpt Fourier transform will be xpj omega. Now how do we come from xpt to this? From pt we saw that the Fourier transform also are set of impulses. Now how do we find out Fourier transform for xpt? For that we use this particular relation that we see here. Xpt is basically multiplication of x of t with p of t. And again here there are few things that I'm going to present, which you may have already seen it, but it may not have been that clear, but now let me make it more clear. Okay, so how do we come from xpt to xpj omega? Xpt is basically x of t multiplied by p of t. Now if we take Fourier transform, what happens? Now left side will become xpj omega. Xt Fourier transform is basically going to be xj omega. PT Fourier transform is going to be Pj omega, and this multiplication sign that you see gets converted into what we call as convolution, circular convolution. One thing we have seen earlier, you may have, you still may remember this, convolution in time domain ends up becoming multiplication in the Fourier domain. This we know from our previous knowledge of properties of convolution or properties of Fourier transform. So this was Hj omega into Xj omega. So convolution gets converted into multiplication. Now if you have multiplication, that's converts into what is known as circular convolution. Now what is circular convolution? It is same as convolution, but just scaling by 1 over 2 pi. At this moment, just take it this way. It is 1 over 2 pi times your actual convolution that you know. So multiplication gets converted to convolution, but scaled by 2 pi. The other few things that you should know about convolution itself, we have seen it earlier. So let's just see the convolution itself. Convolution of anything with delta t or convolution of anything with an impulse will end up giving you the same thing back. You have already seen it. Convolution of anything with a shifted impulse will end up giving you the same thing back, but shifted by the same t naught. So this is very important and very interesting. Now this is where we have variable t. Now once we talk about variable, that means time domain or variable of time. But the same thing is true in any domain. Let's say we have this and convolved with, let's say, Xj omega. This will also give you the same thing back, Xj omega. And similarly, a shifted impulse here convolved with Xj omega will give you the same Xj omega but shifted by omega naught. So these are few things that are going to be helpful once we see what happens here. Now let's try to see what happens here. Xpj omega is basically 1 over 2 pi times convolve with Pj omega. Now if Xj omega is convolved by an impulse, it gives us the same thing back. Convolved with a shifted impulse gives you shifted version. Now let's see what we have here. So here, once we take Fourier transform of this thing, it is Fourier transform of this product, which will be Fourier transform of Xj omega convolved with Pj omega. So Xpj omega is nothing but 1 over 2 pi times Xj omega convolved with Pj omega. This is what your Xpj omega is going to be. And Pj omega we have seen are just set of impulses. Set of impulses which are having value equal to omega s and placed also at multiples of omega s. This is what your Pj omega was. Similarly at 2, at 3, and we have all these impulses. So let's see. That means once we find this out, you will see that the end result would be you will end up getting the same Xj omega shifted at multiples of this, and because of that scaling of 1 over 2 pi, that omega s actually end up becoming omega s divided by 2 pi would be equal to something like 1 over t, because we know that omega s is equal to 2 pi over t. So omega s over 2 pi would be just 1 over t. So this is what we end up getting. Xpj omega ends up becoming this. Okay, so I think we are out of time. So next time I will again start with the same impulse train sampling. Remember, we are going to see three things: what is going on in time domain, what is going on in frequency domain, and the equations for all that. So these three things we are going to cover for impulse terrain sampling. So tomorrow's lecture we are going to cover this slide set number 10, hopefully finish this. And obviously second half, be ready for a quiz also. So two things we are going to do tomorrow. Any questions? So if there are no questions,
topics होगा?
I don't know. I have not made it yet. Whatever comes in my mind, I don't pre-plan the quiz. It is just spontaneous. It will be previous topic. Obviously, I will not use this slide set number 10. It's just a new one. So up till slide set number 9, it's just convolutions and Fourier. It will be related to that. Slide set number 10, we are just covering it. So most likely, rather I can say this, it will not be from slide set number 10. Any questions? So if there are no questions, this is all from my side. Let's meet tomorrow.